Swayam Prabha. Digital India. Educated India.
So, basic solidification mode in welding process can be represented in four different ways. One is that planar, that means the solidification front move in the form as a plane. Next, another mode of the solidification front that can create maybe by breaking the planar interface, and it can create the kind of cellular structure. Okay, and then during the solidification also, that there may be the possibility of formation of the another type of solidification mode, that is called column or dendritic structure. That means, the growth happens in such a way that it makes a big column and the primary and secondary dendritic arms attached with that column. So, this kind of structure also it is obvious from the figure that this structure actually represents the columnar dendritic type structure, and that actually happens during the solidification from the within the liquid metal transformed to the solid phase. So, during that transformation it creates this kind of that means columnar dendritic structure. Of course, the dendritic structure can be formed in the like a equiaxed kind of structure. That means, it is like if you see from the figure that there is a 3 arm and the secondary dendritic arm are spacing accordingly. So, that it looks like the equal amount of spacing in all 3 directions. So, it is a kind of structure or mode is kind of a equiaxed structure, microstructure, what you say almost equal size of the grains throughout the microstructure. So, these are the 4 different types of solidification mode generally observed in case of welding process. Now, in much details solidification in welding process, and it is very much specific to that the alloy materials, basically solidification of the not pure metal. So, maybe we can say that in case of alloy metal, that constitutional supercooling is the one of the important phenomena that is attached with the solidification during the welding process. So, supercooling, we have some idea that from when during the solidification, that when the liquid molten metal comes around the phase transformation temperature, that means from solid to liquid phase transformation temperature. So, during that transformation, and there is a amount of the supercooling observed in the liquid metal. Of course, it pertains with some conditions, that means that before starting of the phase change, the amount, the nucleation mechanism involved in the welding process or maybe solidification process, that actually governed by the what is the amount of the supercooling temperature. That means, the supercooling temperature below the solid to liquid transition temperature. So, in case of pure metal, it can be well defined from the time versus temperature diagram, and this amount of supercooling depends on the, or maybe values are the different for the different types of the material. So, normally the amount of the supercooling is mainly promote that the homogeneous nucleation, or maybe in case of homogeneous nucleation for in solidification process is mainly driven by the amount of the supercooling, which is entirely different from the heterogeneous nucleation mechanism. But constitutional supercooling can be defined in such way that it actually occurs during solidification, and due to the compositional solid changes which finally result in the liquid metal below the freezing point temperature and that exist ahead of the solid liquid interface. Actually, this constitutional supercooling mainly affects or better describes the what is the amount of the supercooling that depends on the compositional solid changes specifically for the alloy material, and that amount of the solidification constitutional supercooling during the solidification in case of graphically we can represent here that this region marked by red color that actually represents the region of the constitutional supercooling, or we can say the amount of the supercooling in case of alloy. But this amount of the supercooling generally exists during the solidification process of specifically the alloy metal, but the mathematical term or parameters that actually govern or may be linked with the constitutional supercooling is that is better described by the one is the diffusion coefficients of the solute in the liquid, that means this DL that represents the diffusion coefficients. If you see the unit of the diffusion coefficient is the length square per unit time. So, mainly it is a diffusibility, it represents the diffusibility of the solute in the liquid metal. Another parameter that actually used to describe the solidification behavior and specific for the alloy material, that is the growth rate. So, that is the unit is that length per time or length per unit time, that is representation of the growth rate, and then temperature gradient. So, temperature gradient is the theta by L, that means it is the temperature per unit length. So, these are the typical parameters that actually involve to represent the constitutional supercooling during the solidification process. Now, we try to explain this phenomena graphically, that first if we look into this first figure, there is a transition of the solid to liquid phase. So, here the growth rate is R, that means growth rate more it is linked that what is the what way that the solid liquid interface is basically moving. So, that zone between the solid and liquid, there is a zone mainly that is called the Mossi zone. So, in this zone the liquid and the solid phase coexists, but this depends on the or in the amount of the supercooling exists within the during the solidification of a specific alloy. Now, if we see the temperature versus concentration graph, here you can see the solidus line is there and then liquidus line and initial composition having the C0. So, this material is subjected to some amount of the supercooling. So, that constitutional supercooling is simply marked by the red color, and that means the temperature difference in this case is delta T. So, that delta T on the temperature axis, it is represented that between the TL and TS, that is the amount of the temperature decrement with respect to the initial composition. And if we see even with respect to on the liquidus line, the composition or concentration of the alloy material, here you can see that C0 by K, that is we represent that C that K equal to ratio of the CS and C0. So, from here we can this here composition is represented by C0 by K. Now, this amount of the constitutional supercooling, if we project in the right hand side figure, here if you see temperature versus distance from solid liquid interface. So, up to what extent from the interface it can go, that is represented simply just projecting this constitutional supercooling on the time versus concentration graph to the time versus distance graph. Here we can see that this is the on the this first slope is the actual slope. The actual slope is the temperature gradient represented by the mathematically represented by term Z, temperature gradient. And then if we look into the other slope, the slope of the tangent at this point here we can see the slope of the tangent can be represented by what is the slope means, the change of the temperature, that means temperature difference with respect to some distance here, but here the distance can be counted maybe in terms of the boundary layer here, that is the diffusivity or DL, diffusion coefficient divided by the growth rate. If you see the dimensionally also, so this term delta T and dl by r, that also represents the slope of the tangent. So, in this case it is very obvious that definitely the actual slope, from the figure also it is very clear, the actual slope g is less than equal to the slope of the tangent. That point of view we have estimated that during the supercooling what is the temperature difference and what is the amount of the distance travelled by the solid liquid interface in terms of the diffusivity and growth rate. So, here if you geometrically or graphically we can see this slope is basically less than that of the estimated slope here. So, to have the constitutional supercooling, so graphically we can say that this condition G by R less than delta T by dl, this condition is satisfying. So, that actually that is the mathematical conditions during the solidification. So, probably having in this case the constitutional supercooling. So, now we will further look into other condition, or maybe we try to explain physically that what is the mathematical condition for the constitutional supercooling and how it can be linked with the solidification behavior during the welding process. So, first comments is that of course, the shaded area that represents the constitutional supercooling, therefore, that region is consists of actually liquid alone is unstable. So, in that zone basically solid and liquid coexists. Now, to estimate that slope also we assume that the thickness of the boundary layer during the movement of the solid liquid interface at the steady state condition is better described by the dl by r. dl is the diffusivity divided by the growth rate, and that dimensionally it represents the length, dimensionally it represents in terms of length dl by r. Now, to avoid constitutional supercooling, we can put the condition just reverse having the constitutional supercooling. So, having the constitutional supercooling, this was the condition G by R less than delta T by dl. What to avoid constitutional supercooling, it is just G by R should be greater than equal to delta T by dl. These are the to avoid the constitutional supercooling. So, this mathematical condition is sometimes helpful to quantitatively explain the solidification behavior, that what are the driving mechanism, whether constitutional supercooling exists or not, based on that type of nucleation, whether it is homogeneous and heterogeneous nucleation, that is better explained by these mathematical conditions. Now, the constitutional supercooling can also be explained in can also be used to explain whether there is a need or breakdown of the solid liquid interface can be stable interface from the planar solid liquid interface. That means, planar solid liquid interface is stable if not having the constitutional supercooling, that means just opposite to the condition of the avoiding the constitutional supercooling. So, in that sense G by R greater than equal to delta T by L, that actually represents for the stability of the planar solid liquid interface. Now, in planar solid liquid interface it may break also, and due to the cellular or maybe in the dendritic, so that solid cell or dendritics actually can coexist with the intercellular spaces or interdendritic liquid. So, that breakdown of the planar solid liquid interface to other solidification mode, cellular type or dendritic type, that dendritic type, that can be explained mathematically here also in terms of this G, R, delta T and dl, all these parameters. So, higher G and lower R, that actually leads to the planar solid liquid interface. That means, if we look into the condition also that G by R ratio is very high, that means there is a existence of the solidification mode in terms of the planar solid liquid interface. Other side, higher delta T, that means temperature difference is very high. So, that means degree of supercooling is very high, and of course, more amount of the diffusivity dl, that actually leads to the more difficulty for a planar solid liquid interface to be stable. So, that actually breaks down the stability of the solid liquid planar interface during the solidification process. So, here we can say mathematically that two things, if G by R less than delta T by dl, that means there is a existence of the constitutional supercooling, that means non-existence of the planar solid liquid interface in this case. Other way also, if G by R is greater than delta T by dl, that means there is a existence of the, or that is a favorable condition to put the solidification mode in terms of the planar solid liquid interface. Now, here we can look into the different type of the solidification mode and structure. So, it is also necessary to mention that although these two parameters G and R, so G and R, these two parameters, that means temperature gradient and growth rate, they actually mathematically define the mode of the solidification at the same time, and also define the rate of the cooling. That rate of the cooling is decides basically that whether it is fine structure or whether coarse structure exists during the produced during the solidification process, and solidification mode decides what is the type of the, whether it is planar, four types of the planar or cellular, dendritic, columnar dendritic or equi-X dendritic kind of structure. Now, if we see that four different types of mode is better, from this figure we can see that there is a four type of solidification mode: planar mode, cellular, columnar dendrite, equi-X dendritic structure. Now, here you can see that increasing the constitutional supercooling is transform the structure from planar. So, that means very low amount of the constitutional supercooling promote to the formation of the planar kind of the solid liquid interface. But if the constitutional supercooling is very high, maximum in this case, they actually promote the structure like equi-X dendritic structure, it will try to produce. Now, graphically also we can see that here the vertical line, the solid liquid interface, and that side the equilibrium temperature reach, and this represents the actual slope in the curve. So, in the that curve, the time and the solid liquid the distance versus temperature, in that case the actual slope. So, here if you see that the temperature and actual slope, they are not interfering with respect to each other. That means, there is a minimum amount of the, or we can say there is no constitutional supercooling exist. So, that promote the planar kind of the solid liquid interface. The mode of the solidification is basically planar. Next, if the certain amount of the increment of the constitutional supercooling, then it cross the slope is less basically, and then there is a shaded zone that is marked by the black, the shaded zone, and that actually produce the cellular kind of the solidification mode. Cellular mode, in this case, that means there is a small amount of the constitutional supercooling exists. If you look into the third, that amount of the constitutional supercooling actually increasing, and that try to produce the columnar dendritic structure, and finally, the maximum amount of the supercooling that produce the equi-X dendritic structure. So, depending upon the amount of the constitutional supercooling, the solidification mode basically changes, or solidification mode can be decided. Now, here also other comments that the dendrites and the liquid phase coexist is called basically the Mussey zone. So, in that zone where the dendritic formation of the dendrite and the liquid they actually coexist, that is the normally called the Mussey zone, and that Mussey zone is basically in between the temperature between the solidus and liquidus temperature. So, at very high degree of constitutional supercooling, it is very obvious that the Mussey zone becomes very wide. So, that zone becomes very wide, or at the other way, if low degree of the constitutional supercooling, there is almost no Mussey zone, or Mussey zone not very wide, small. So, here from that with respect to the point of the view that with the degree of the constitutional supercooling, we can predict at least the what are the type of the solidification mode, whether it is planar, cellular, columnar dendritic or equiaxed dendritic structure. Now, here we like to mention that the two parameters, the temperature gradient G and the growth rate R, affects the solidified microstructure. So, two different ways. So, by combining these two parameters, the temperature gradient and growth rate, here you can see the product of G into R, this actually known as the cooling rate. If we dimensionally check it, then that G is the temperature gradient, temperature by length, and R is the growth rate. So, length by time. So, in that respect, the length by time is basically temperature by time, that actually represents the cooling rate. At the same time, the ratio G by R actually determines the solidification mode, that already we have discussed, that depending upon the G by R ratio, we can define the mode of the solidification. So, this combining these two G R and G by R, if you try to represent the one axis, the x axis the growth rate R and temperature gradient is the y axis, it is the G. So, this combining these two, we can find out that different solidification mode this way, that planar, cellular, columnar dendrite and equiaxed structure. So, high G by R value, that actually promote the kind of the planar structure, or at the same time low G by R ratio, that actually promote the equiaxed dendritic structure, dendritic solidification mode. But if you see that from the graph also, if now we try to incorporate the effect of the cooling rate also. So, here this line that represents the rate of the cooling, so G R, and so first line alpha 1, that represents the low cooling rate, and if you see the alpha 2, the second line, this is represents the cooling rate on this graph, that represents the high cooling rate. So, if cooling rate is very high, overall microstructure is very fine. If cooling rate is low, the overall microstructure is not the coarse structure. So, basically higher cooling rate we can expect the fine structure, and lower cooling rate we can expect the coarse structure. So, greater G R, G into R, that means G into R, that means greater cooling rate, that we can find out the very fine solidified cellular kind of dendritic structure. If we see from this figure also, that most of the structure exists in this case, that either cellular or columnar dendriting, and planar and equiaxed is the more two extreme cases here, but in general cellular and columnar dendritic structure exist, and it becomes more finer structure if cooling rate is very high. That means, it is beyond that zone, the second line corresponds to alpha 2. So, basically alpha 1 equal to 1 G 1 R 1, or alpha 2 is basically another value of G into R. So, from this figure we can explain also quantitatively that whether it is fine structure, coarse structure, at the same time what is the solidification mode, or what is the solidified structure, whether it is very planar, columnar kind of structure, dendritic, equiaxed, and all this kind of information we can get by analysis of this kind of figure. Now, after solidification mode, we will try to look into the discussion on the weld microstructure. So, grain structure actually affects the susceptibility of the solidification cracking. So, it is very much linked with that, and finally, grain structure also define the mechanical property. So, it is it is necessary to link that what is the final microstructure and probably what is the expected mechanical properties, or whether there is any solidification cracking may occurs or not. That kind of information can be get if we analyze the mechanism of the grain structure or maybe weld microstructure formation during the solidification process. So, one important aspect of the growth in the fusion zone of the welded structure, that is called epitaxial growth at the fusion boundary, and this epitaxial growth basically happens in case of the autogeneous fusion welding process. So, if we use some filler material that actually destroy the epitaxial growth mechanism, maybe in that case some other mechanism can be better to explain the phenomena of the grain growth. So, epitaxial growth, we can see that molten metal first is in contact with the solid with the base metal, then grain growth initiates on that boundary or at the solid liquid interface, and it proceeds towards the weld central line. From the figure also it is very seen that very obvious that welding direction is there, and the weld pool, from the weld pool liquid weld pool, and that interact with the base metal. So, from that interface it growth happens one particular direction. So, that this type of growth is basically called the epitaxial, first nucleation and then growth. So, if you see that FCC, BCC crystal structure, they have the kind of columnar dendritic structure actually grow in the 100 direction. So, Miller index of this 100 direction. So, that actually observed in case of FCC and BCC material. Now, if you see here that if you use the filler material, then weld metal composition changes, and that actually leads to the different type of the crystal structure for the weld and the base metal. So, that adding the filler material does not promote the epitaxial growth, and then new grains and nucleates basically forms at the fusion boundary when there is a addition of the other alloying elements, or maybe you can say that with the addition of the filler material during the welding process. So, during solidification the grains tends to grow perpendicular to the weld pool boundary, but the reason for that, there is a maximum temperature gradient actually exists along this direction, and then sometimes the columnar dendrites or cellular cells or cellular structure within each grain also grow in the within grain that try to grow in the easy growth direction. So, that means that different type of crystal structure material having the easy growth direction. For example, the FCC structure, the 100 is the easy growth direction, and we can observe specifically for the aluminum alloy and austenitic stainless steel, they are having this direction. BCC material also having the easy growth direction is 100, that is why if you look into the one unit cell, the 100 is basically along the one of the edge, along the edges. So, the carbon steel, ferrite, stainless steel, this type of materials also having the easy growth direction for the BCC material as the along the edge of the unit cell, that means 100 direction. Then in case of hexagonal close pack also having the easy growth direction, and that hexagonal close pack structure titanium and I think magnesium, and body center tetragonal structure tin also having the easy growth direction is 110, that means along the phase diagonal of an unit cell. So, different type of materials may have the different easy growth direction, and typically the epitaxial growth nucleation, not only growth, maybe first nucleation starts and then growth process starts. So, that epitaxial growth mainly happens probably the pure metal and during the welding process, and that along the normal to the phase boundary, because the driving force, the epitaxial growth in specific direction probably the maximum temperature gradient along that direction. But the conclusion from here is that if we add the filler material, then the epitaxial growth may not be possible in that case. Now, what are the effects of the welding parameters on the grain structure? And just if we try to look into that is that if you look into the actual welded structure, what type of microstructure we can expect during the welding process at very high speed probably and at very low speed. So, if we see that high welding speed, the typical nature of the weld pool forms, that is the elongated weld pool, or sometimes teardrops can also form. So, if you look into the first figure, that it is a high speed, that if it is a elongated weld pool looks like, and when the heat source is moved one specific direction during the welding process. So, here the growth or grain actually grow with respect to that weld central line and almost perpendicular to the weld central line, but if it is very high speed, then it becomes axial, exactly perpendicular to the weld central line. And if we gradually reduce the welding speed, that means if very low speed, it takes the curvature and with respect to the weld central line. So, and from that weld central lines make a curvature and goes towards the outer periphery of the weld pool. So, these are the typical grain structure generally observed during the welding process. Now, if in case of low welding speed, the welding pool looks like the elliptical form, and trailing pool of the boundary of the teardrop shape, that means it is a very high welding speed, the weld pool is almost very nearly straight and the growth also happens perpendicular to that. But columnar grains forms during these things almost the straight normal to the pool boundary. But in case of low speed, since the trailing boundary is of elliptical shape, then weld pool is basically make a curvature or make a curve, and the columnar grains are also curved in order to grow perpendicular to the weld pool boundary. So, making the initial curve, so that and finally, it makes the final curvature, it is like that almost perpendicular to the weld line. So, these are the typical weld grain structure that actually observed during the welding process. Now, we look into that weld metal nucleation mechanism. So, there is a nucleation mechanism, basically the mechanism of nucleation actually controls the microstructure of the weld pool. So, we need some understanding on the nucleation mechanism actually prevents during the welding process. So, two things are there. If you see actual welding process, that first is the growth of the columnar grains is basically interrupted by the formation of the new grains. So, new grains, formation of the new grains, they interrupt the growth of the columnar grain, and we see the growth of the columnar grain is actually the rear observed normally in the rear side of the weld pool. In the other way, when the new grains form and that actually disturbs the growth of the epitaxial grains is interrupted. So, that disturbs the growth of the epitaxial growth of the grains also with the formation of the new grain. So, these two phenomena is counteracting with respect to each other. Then new grains normally are often equiaxed rather than the columnar kind of the structure. So, new grain forms here during the welding process, most of the we can find out it is almost the equiaxed structure rather than the columnar kind of the structure. Now, if you see the dendrites in the, if you see the dendrite, the Mussey zone behind the trailing portion, that means rear part of the weld pool, and in this case the mechanism of nucleation is basically depends on the several phenomena. One thing is the dendritic fragmentation. So, here if you see that dendritic fragmentation is happens because on the trailing side, the rear side, of the oil pool, there is a formation of the dendrites, and the due to the convective flow of the liquid metal within the oil pool, that actually brings the two mechanism, that means fragmentation of the dendrite. At the same times, the partially metals can be detached from the grains. So, these two promotes the formation of the heterogeneous nucleation most of the cases at the trailing side of the oil pool. So, the mechanism of nucleation during the welding process is better explained. One point is that dendritic fragmentation, then grain detachment, and that actually mainly promote the heterogeneous nucleation process. So, this figure also if we see that dendritic fragmentation, grain detachment is very obvious. So, and that is that travel from one point to another point is due to the only the convection of the molten metal. And here also other way that sometimes the nucleation mechanisms is basically driven by the